Welcome to Spring LIB.
Okay, so here's a free body diagram of the merry-go-round. We see that the force F is applied tangentially to the merry-go-round, and then because of that, there is some angular acceleration alpha, and the radius of the merry-go-round is r. Now we need to find out omega from this setup. Now we know that initially the merry-go-round is at rest, so omega, and if we call it omega naught, that's going to be 0. So this is the initial angular velocity, which is 0. And we have to calculate final angular velocity from this problem. So to do so, we can start with the torque equation, where we know that torque is equal to moment of inertia times alpha, and we're already given the moment of inertia for the merry-go-round. And from this setup, we can see that torque is basically force times the radial component or radial vector. So torque is F times R. So we can put that equal to I alpha. That's what we did here. And from there, if we solve for alpha, we see it's Fr over I, where force is given as 18 newtons, R is 2.4 meters, and I is 2100 kilogram meter squared. So using those numbers, we see alpha, or the angular acceleration, is 0.02057 radians per second squared. Now to figure out omega, as we mentioned that the initial angular speed is 0, so we can get set this guy equal to 0. So we'll have omega equals alpha times t, and again this is equivalent in the linear motion, where we say v, or the final velocity, is equal to u as in initial velocity plus a times t, where a is the linear acceleration and t is the time. So this is the linear equivalent of this angular equation. So alpha is this guy right here, and t is given as 15 seconds. So using those numbers, we see omega is 0.309 radians per second. Now in the second part, or part B, we need to figure out how much work did the child do on merry-go-round. So there are two ways to do this problem. I'll work out the first one, and I'll give you a hint to do how to do the second one, and you can do it on your own and verify whether the work done is same for both of the processes or not. Because no matter what process you use, you should end up having the same number. Now, one that I chose to do is from the energy perspective. So the total work done is the final kinetic energy, we call it K2, minus the initial kinetic energy, we call it K1. And we know that the difference between the kinetic initial and the final kinetic energy is equal to the work done by the child, because there are no other forces than the force that is applied by the child. So the initial kinetic energy is 0, and the reason for that is because the merry-go-round was at rest, so there's no initial velocity, so we can set that to 0. For the final kinetic energy, we can say that K2 is equal to half of I omega squared, where I is the moment of inertia, omega is the final angular speed, which we calculated here. So using I and omega, we see that K2 is 100 joules, and as we can see here, W is equal to K2, so the work done will be 100 joules. Now let me talk about the alternate method. So for the alternate method, we can use the following formula. So here work done is equal to torque times change in angular position, which we call as delta theta, where torque is we can calculate torque from this part, F times R. We know R and F, so we can calculate torque from there. And for delta theta, we know that this quantity right here is theta minus theta 2, where theta 0, where theta 0 is the initial position and theta is the final position, and that's equal to omega naught t plus half alpha t squared. And this guy is 0 because initial angular speed is 0. So theta minus theta 0, or delta theta, is half alpha t squared. So we know alpha, we know t. So if we put the numbers here, we will get delta theta. So if we multiply delta theta with the torque value, we should get 100 joules as our answer. So that's an alternate method that you can try and see if that matches this value or not. Now in part C, we have to find out the average power supply, power supplied by the child. So average power supply is change in work done over change in time. So we know that the change in work is 100 joules because energy changed from 0 to 100 joules, and that's the total change in work done. And delta t, or the time period, is 15 seconds. So if we divide 100 by 15, we get 6.67 watts, and that's the average power supplied by the child. Thank you.